So we've seen that if A is equal to Q times R, that projection problems become much easier because projection onto the column space of A is then just Q times Q transpose, and we don't have to bother with any inversions. Now I want to argue to you that if A is equal to Q times R, that least squares problems become much easier as well. Here's the theorem that argues that. So let's say A is Q times R, and let's think about the least squares problem, which is Gramian of A times X hat equals A transpose times B. Well, remember that one of the properties of QR factorizations is the common Gramian property. The Gramian of A in A equals QR is the same as the Gramian of R. So I can replace A transpose times A here with R transpose times R. I can also substitute in A equals QR on the right side of this equation to get R transpose times Q transpose when I distribute the transpose. So now the least squares problem, which starts as Gramian of A equals A transpose times B, can be rewritten as R transpose R times X hat equals R transpose times Q transpose times B. And finally, if A has full column rank, one of the properties of QR factorizations is that R is non-singular under the condition that A has full column rank, which in our context here would mean that we could cancel the R transpose on the left, and we end up with a simplified version of the least squares problem, which is R times X hat equals Q transpose times B. So when A equals QR, the least squares problem simplifies to R times X hat equals Q transpose times B. And this is great because remember that R in a QR factorization is an upper triangular matrix, so we can very quickly solve this least squares problem by using back substitution. So that's the upshot. We now have two forms of the least squares problem. If I don't know anything about A, I can still write down the least squares problem, and it will be A transpose A times X hat equals A transpose times B. But if I have a QR factorization, I know my least squares problem will reduce to R times X hat equals Q transpose times B. With the QR factorization, the simplified version of the least squares problem is much more quickly solved with back substitution because R is upper triangular. So let's look at an example of this theorem playing to our advantage. Here we have a QR factorization of a matrix A. So here A is this 4x3 matrix, which I've factored as Q times R here. And someone is giving me a vector B here. Well, if I wanted to, I could study the original least squares problem, which is Gramian of A times X hat equals A transpose times the vector B here. But I don't want to do that here because I have a QR factorization, which makes my life a lot easier. So the original least squares problem, Gramian of A times X hat equals A transpose times B, reduces to R times X hat equals Q transpose times B in this situation. And if I look at R times X hat equals Q transpose times B, I can simply just write that system down. Here on the left here, you're looking at R times the vector X hat. So the coefficients in this in the coefficient matrix here are exactly coming from the R in the QR factorization here. And then to the right of the equal sign, what you're looking at is Q transpose multiplied by the vector B that we're starting with here. And how do I solve this system? Well, I start from the bottom because this is an upper triangular system. The last equation is straight up telling me that x3 hat equals 1. So I can then go to the other equations in this system and replace x3 hat with the number 1. Then I can go to the second equation of the system, and here I can solve for x2 hat. When I solve for x2 hat, I get 0, and then I can replace all of the other equations, x2 hat with the number 0. Now I can go to the first equation and solve for x1 hat. When I solve for x1 hat here, I end up getting 1, And that gives me the least squares solution. This automatically tells me now that x hat here is equal to 1, 0, 1. And I haven't had to do a single row reduction throughout this entire process. So because someone is giving me a QR factorization here, they're making my life a lot easier when I study the least squares problem.